Welcome back to ECE 442-542. This is the second component of lecture 7.1. We are trying to motivate the need for more rules for sketching these root loci. And the first three rules are beginning and ending segments of the root locus, the real axis segments that belong to the root locus, and where are these breakaway and reentry locations on the real axis. What we want to now motivate in this video or in this lecture is Rule 4 and Rule 5. Rule 4 tells us how to determine asymptotes, construction asymptotes that allow us to sketch the root locus branches that go off to infinity. Those construction asymptotes help guide us in how to sketch those branches of the root locus that are approaching those zeros at infinity. And rule number 5 is concerned with poles or zeros that are complex. If we have complex poles and our root locus starts on the poles, in what direction, at what angle does that branch leave that complex pole? That's the departure angle. If we had complex zeros, at what angle does the root locus branch that's terminating on that finite zero, what's the arrival angle, or the angle that it arrives at that zero? Let's now see why, well, hopefully you can understand maybe why we need Rule 5, because we haven't dealt with complex poles or zeros yet, so that's an immediate reason for needing Rule 5. And Rule 4 is because we've only looked at a pole zero excess of 2 or less, and we'll see then that when we have more poles or 3 or more poles than zeros, we're going to need something beyond what we've done so far. Let's just kind of remind ourselves what we can do, where we have been with this root locus strategy. Let's start with one example. Suppose that we now have a pole at 1. So here is our closed loop pole, and I actually wanted that to be a blue pole. And now what's the root locus for that particular system? And the root locus, remember, that's the values in the complex z-plane that could potentially be closed loop poles in our normal unity output feedback configuration. Here is our plant, 1 over z minus 1. We are now introducing this adjustable parameter k. Think of that as our knob that we can now turn from 0 up to infinity. And we want to know, as we're turning that knob k from 0 to infinity, what are the possible closed loop poles in this diagram. Some of those might be unstable, but the root locus now tells us all the potential closed loop pole values. We know from Rule 1 that we start at z equal to 1 in this case. Rule number 2 tells us which of these two line segments on the real axis belong to the root locus, and that's because we know that the angle on that segment that belongs to the root locus has to have an angle of minus 180. Any point here satisfies that angle condition, because the angle now is measured from the positive real line emanating to the right or moving off to the right from that pole, and the angle to get us to any of those points is 180 degrees. So we now know that this is all there is to the root locus diagram for that particular system. That's now all potential closed loop poles, and we know hopefully that some of those, if we cranked up the gain too much, we are going to go outside the unit circle. We are still worried about keeping all of our branches of the root locus simultaneously inside the unit circle. In this case, the way to do that, I hope you see, is to make sure that you don't adjust that knob, that K, value beyond the setting of that k that would produce a pole outside of that particular unit circle. And we can find that from knowledge that we already possess. We know the closed loop transfer function for that unity output feedback and its negative output feedback configuration is kg over 1 plus kg. That's block diagram algebra. The closed loop behavior is determined by the denominator set equal to 0. That gives us our characteristic equation. We can solve that for kg by subtracting 1 from both sides, and the gain condition, and minus 1 is 1 at minus 180, so we know that the magnitude of that expression has to equal 1. That's the gain condition. Our gain is k, our plant g of z is 1 over z minus 1. That magnitude has to equal 1. We can now evaluate for k at any point on the root locus to determine what we need to crank that gain up to get us to a particular location. We might want to crank the gain to get us to that point, or we might want to crank the gain to get us to that point. We know that if we crank the gain too much and get beyond that square, our closed loop system will be unstable. We know the gain is now determined by this magnitude of z minus 1 from the gain condition, or the magnitude condition. If we now evaluate that at z square, or at minus 1, we now can determine the actual value of k for stability. We now know that for our system that we just started with to remain stable, we need k, and maybe in this case we want to move it off the unit circle. We want k to be between 0 and 2 to produce a stable closed loop system. That we can do from the very first two root locus rules provide us with that root locus diagram. Let's move on from that. Suppose now somebody gives us a two-pole system. We now have a pole at 1 and a pole at 1/2. And I hope you can now determine the root locus for this set of poles and zeros. You can subdivide the real line into 3 segments, and I hope that you see that in that segment we have one pole to the right of that segment. This pole goes to the right, this pole goes to the left. We have 2 branches, we have 2 closed loop poles. Those can't just terminate, they now move away from each other in a manner that splits the z-plane. Those now go off at plus and minus 90 degrees, and because these poles were at 1/2 and 1, we now know that they come together halfway between those two, and we can use that information now to determine what it's going to take to get us to that particular point. This is now z delta. And we know the real part of that is halfway between 1/2 and 1, so that's 3/4. What we may not yet know is what's the vertical distance to get us to that triangle location. And then once we have that value for z delta, we can use that to solve for the k to determine our upper limit of stability. In this case, we know that the magnitude of z delta is equal to 1 because it's on the unit circle. If that's the case, we now know that we can say that since z delta is equal to 1, that now says that the real part of that z delta location, 3/4 squared, plus the vertical distance, y squared, is equal to 1 squared. we can now use that to solve for y. We now know that y squared is equal to 1 minus 3/4 squared, or y is now the square root of 1 minus 3/4 squared. We can now use that to determine what y is. Y is now the square root of 1 minus 9/16, or it's now the square root of 7/4, and if we calculate that, that's 0.6614. We now know what z delta is. Z delta is 3/4 plus and minus j. We have to have these in conjugate pairs, 0.6614. And we know from the magnitude condition that k over those two, or k times g, which is now k over z minus 1/2 and z minus 1, has to have a magnitude of 1, or k is now this product of pole factors. And we can find the upper limit of stability, which is k, let's say, sub delta. That's going to be when we evaluate this gain formula at z equals z triangle, which is now 3/4 plus j, 0.6614. Or that's now 3/4 plus j, 0.6614 minus 1/2, times that same z value minus 1. And I think you can see that those are the same length. We have 1/4 plus j, 0.6614, times minus 1/4 plus j, 0.6614. So we have 1/4 squared plus, or the real part squared plus the imaginary part squared, square rooted to get the magnitude, but we have that same expression on the second term, so we really have this, and if we compute that, we end up with k being equal to 1/2. So now for stability, based on what we now know for sketching root loci, we now know that to produce a stable closed-loop system, we can have k living between 0 and 1/2 if we apply a unity output feedback configuration to this particular system again. Again, we're assuming that we have that closed-loop diagram. So now we know how to create stable systems. What about if we make it a little bit more interesting? We went from 1 pole to 2 pole. Let's make it now a third pole. Suppose g of z is 1 over z, z minus 1/2, z minus 1. We now have a pole at 1, a pole at 1/2, and a pole at 0. And I hope that we can now fairly quickly determine that we have a segment there between 1/2 and 1, and we have another segment there between 0 and minus infinity. Those are our segments. How many branches do we have? We actually have 3 root locus branches. We have a branch that starts there. We have another branch that starts there. They go towards each other. This branch just keeps going to the left. Now what happens when these two go off? They actually do not go vertical like we had with just 2 poles. Now, in fact, what we have is we have 3 poles, and the branches really need to sort of split the complex z-plane into equal parts as they approach infinity. So in fact, this is going to break away, and one's going to go up here, one's going to go down here, and if they're now at infinity, our asymptote construction lines are going to be such that they tell us how to split this complex plane into equal regions. And I hope you can see now that this angle is the same as this angle, and that's the same as this angle. So we are splitting this z-plane into 3 equal pieces. We now have 360 degrees divided by the pole zero excess of 3. Those branches are now separated by 120 degrees. And what we're going to learn then is where these branches that are going off to infinity, how do we know that they get there? That's now rule number 4 in our root locus strategy. Here we know that we have just the equal part above the real axis as below, so this acute angle is 60 degrees, and so is this one, because we know that they're each. So those asymptote sketching angles that are dashed, those are at 60 degrees relative to the positive real axis. Okay, there's rule number 4. Where's rule number 5? Well, now suppose that we have a transfer function that possesses complex poles. What do we have now? We now have 2 poles at 1/2 plus and minus j 1/2. We have a 0 here. Can you tell me now anything about the root locus so far? Well, yes, you can still use rule 2 to determine that this segment of the real axis belongs to the root locus. How many root locus branches do we have? We have 2 poles, so we have 2 root locus branches, and actually on this segment that's on the negative real axis, we have 1 branch going to the finite 0 and another branch going off to infinity. What we want to figure out is how do we end up on this negative real axis. We start on the poles, so now how do we depart from the poles with our root locus? Do we go like this? And in fact, this is sort of this 2 poles to the right of 1 0 structure. But if we didn't know that, we could now use rule number 5, and rule number 5 is now concerned with if this is now tangent to that root locus branch that's leaving, we want to be able to calculate what is this alpha sub d, this departure angle, and in fact these are symmetric, so this angle would need to be the negative of that alpha sub d. They should be the same, and so this sketch should be symmetric relative to the positive and negative z-plane. Here we had a pole 0 excess, just to sort of summarize what we've seen, of 2 minus 1 is equal to 1, so we actually only had 1 branch of our root locus going off to infinity, and it goes off to minus infinity. That branch needs to divide the z-plane equally, and to divide 360 degrees equally, that's 180 degrees. How many root locus branches did we have? Hopefully you see that we had 1 that went here, and I don't care if it goes there or goes in, and we had another branch. We have as many root locus branches as we have open loop poles. In this case then, how many root locus branches? We had 2 open loop poles, and that means that we have 2 root locus branches, and I've highlighted those, 1 in yellow and 1 in blue. One more example to try to, and this is now how these depart from the poles, that's rule number 5. What's the departure angle? Can we calculate that alpha sub d? In this case, it looks like it's about 120 degrees. If it was 90 degrees, then we would be going vertical as we departed from that pole. If it was 0 degrees, then we would be coming off to the right as we departed from that pole. One more as promised, and then we'll get into those rules. But so let's say now we look at the other situation, which is where we now have complex zeros. What does this produce? Now in the complex z-plane, we have a pole at the origin, we have a pole at 1/2, and we have a pole at 1. And the roots of that numerator are imaginary. We now have zeros at plus and minus j. So our zeros are up here. Maybe I should make those zeros the same color as our plant poles. We still can get quite far with respect to our sketch. We know this segment belongs to the root locus, and we know this segment belongs to the root locus. How many root locus branches do we have? We actually have 3 because we have 3 poles. We have a branch here that goes to the right. We have a branch here that goes to the left. This one's going to the left. What we want to know is how do these, we know how to figure out where they break away. That's the relative maximum between those two. Let's just say that they break away here. And now do they come in that way to those finite zeros? Again, this has to be symmetric. And we would then be calculating relative to this positive real line and this tangent line to the root locus, we would say, what's that particular angle? That's now our arrival angle. So that also is going to be a rule number 5, will allow us, the root locus rule number 5 will allow us to calculate or determine that alpha sub a. Again, we had 3 branches. 1 goes off to infinity. 2 actually terminate at those finite zeros.